Okay, so in the previous video, we addressed the scenario of balanced forces, right? Balanced forces. And we said that this formula, which is actually Newton's second law, it tells us a story. It tells us a story when we look at it in this form. So usually it's Fr equals to ma, but when we put it in A equals to Fr over m, which is the same formula, just arranged differently. I always found this more meaningful because it tells a better story, right? What is the story that it tells? It tells us what an acceleration depends on. So we know that if the forces are balanced, the resultant force is 0, and if the resultant force is 0, then the acceleration is 0. There's no change in motion, right? But what if there is a resultant force? That's what this video, this particular LO and this video is about. I mean, it's also the previous LO, but anyway, yeah. What happens when this resultant force? So actually, what is the story that this formula tells us? It tells us what acceleration, the acceleration of an object depends on. Right? It depends on two things. It depends on the resultant force and mass, and we're gonna look through these questions to talk about it. Okay. So, but basically, this addresses unbalanced forces. I'm sure you know what unbalanced forces look like. Basically, any of these scenarios where the force is stronger on where the force is not balanced by another force like this. Okay. So yeah. So unbalanced forces, that means that your resultant force is not 0. And if your resultant force is not 0, this tells you that your acceleration will not be 0, right? Because if this is not 0 on some object with any mass, the acceleration won't be 0. That means there will be a change in motion, and that could look like speeding up, slowing down, or changing direction, right? But there will be a change in motion. And so back to the story that this formula tells us. It tells us what affects the acceleration, and the first thing is the resultant force. So the larger the resultant force, the larger the acceleration. That's right. So let's look at the first question. I'm sure most of you guys could handle this. I'm going to go really quick. Which pair of forces acting on the object causes the greatest acceleration? So you're looking for the one with the largest resultant force. So how do you find resultant force? You don't just simply add up the numbers. The direction matters. Okay. So this is 80 to the right, 20 to the right. So the resultant force is 100 to the right. So I'm just going to show you what the resultant force is. It will be 100 newtons to the right. Okay, so resultant force is usually drawn with double arrow. So this is the resultant force. Resultant force is not an actual force acting on an object. The resultant force is the force that is the result of all the forces acting on the object. So in other words, this scenario here, 80 newtons, 20 newtons, would be the same as will have the same result in terms of the acceleration as an object with a force of simply 100 newtons to the right. These are two different scenarios, but these two different scenarios has the same result. Oops, what happened there? Has the same result. And what is that same result? That same result is that the acceleration will be the same. Okay? So that's why it's a resultant force. So resultant force is 100 newtons to the right. Okay, what's the resultant force of this? The resultant force of this will be 120 newtons to the left. So, it's going to overlap, but it's okay. 120 newtons to the left. What about this? This is going to be 80 to the right, 20 to the left. So 80 minus 20, it will be simply 60. Oops. And this would be 80 to the left, 40 to the right. So just simply 40 to the left is the resultant force, right? I take 80 minus 40. So the largest resultant force is C, and because C has the largest resultant force, you can see that the largest resultant force, if the resultant force is larger, acceleration is larger. So it will have the greatest acceleration. Okay, so this is the first part of the story that this formula tells us, that the larger the resultant force, larger acceleration. What else affects how something accelerates? Right? How something changes state of motion? Well, this formula tells us two things, the resultant force and its mass. So let's look at the next question. Trolley X and trolley Y are joined by a stretched spring. Trolley X has twice the mass of trolley Y. Okay, so when the trolleys are released, initial acceleration of X is 2 meters per second squared to the right. What's the initial acceleration of trolley Y? So how does mass affect acceleration or the change in motion of the object? The larger the mass, what happens? The larger the mass, the lower the acceleration, right? They're inversely proportionate, right? So if this guy goes up, this guy would go down, right? Divide by a bigger number, acceleration will be smaller. So the story that this tells us is that the larger the mass, the harder it is to accelerate, right? And that makes sense because we know that mass is in the larger the mass, the larger the inertia, the harder is it to change the state of motion, right? So trying to move like an elephant, it's gonna be really, really difficult versus trying to move a flick away an end, right, with the same amount of force. So let's look at this now. So if y, you can see that y is half the mass of this, right? So if this is 1, this is 1, this guy is 1. So the total here is 2 kg, say, just for example, and this will be like 1 kg, right? I'm just giving a random number for you to see better. So what's the initial acceleration of trolley y to the left? We know that it depends on the mass and it's inversely proportionate. So if this guy is 2 meters per second square, if this is 2 meters per second square, this would it be twice or would it be double? It's less mass, so its acceleration should be twice, so it's d. Of course, one thing that you're expected to know here is that the force between them is the same because they are stretched by a spring. So the tension in the spring that is pulling them together is pulling them with the same amount of force on both sides. So whatever F is, both are being pulled to the center by the same F because it's tension in a spring. Okay, so that's kind of like background knowledge that you need to know. But the main thing that this highlights again is that if the mass is less, it will accelerate more, right? So if this is half the mass, the acceleration is twice, which is the story that this formula tells us. All right, and of course, finally, actually using the formula of Fr equals to ma, which usually is written like this. Okay, some of you, your teachers teach you to write Rf, that's fine as well. Okay, so Fr equals to ma. We're going to use this in the question 13. So question 13, a block of mass 6 kg is pulled across a rough surface by a 54 Newton force against a friction force. Okay, what is, they give you the acceleration, what is the value of F? Okay, so you need to be very clear that it is not just any F equals to ma, it is the resultant force equals to ma. Why is that significant? What is the resultant force in this picture? The resultant force in this picture is 54 minus F. Can you see? Right? If I were to ask you to find resultant force acting on this object just by looking at this picture, you would tell me the resultant force is 54 minus F. Right? So I'm going to write 54 minus F is my resultant force, F being friction. Right? And then my mass is 6 kg and my acceleration, they tell me, is 6 meters per second square, sorry. So this is my acceleration, right? So probably shouldn't have written here. Okay, I'm just gonna write over it. So this is 36, 54 minus F. Okay, from here it's just math, right? So F equals to 54 minus 36, which would look like 18 newtons, right? I hope that's right. So answer is B. Okay, so the main thing about this question that I wanted to highlight with this question is that it is resultant force, and you need to know that it is the resultant force, not just simply 54 equals to ma, but 54 minus F. Okay, so that's how you find F. That's Newton's second law.